Good morning to all. I am Dr. Sarala, Associate Professor of Mathematics, A.D.M. College for Women, Nagapattinam. I am taking the measure on the real line. First, the introduction of the measure, and that is in mathematics. The measurement in mathematics, the measure is the generalization of measure is called, that is length, area, volume, all these are etc. Now we will see the measure on the real line, that is Lebesgue outer measure definition. The first definition is the Lebesgue outer measure or outer measure of the set is given by m star of A, which is equal to infimum of summation of L of in, where the infimum is taken over all finite or countable collection of intervals in such that A is contained in union of in, that is the collection of intervals. In is nothing but the collection of intervals, and then A is the set, one of the measurement set. The next one, next theorem, prove that m star of A is greater than or equal to 0. The first concept is m star of A, which is equal to infimum of summation of in. In is nothing but the interval, L is the length of the interval, L of in is the length of the interval. This is nothing but the definition of the outer measure. This is always greater than or equal to 0 because the measurement is greater than 0. So it is positive. The next second one, m star of 5, which is equal to 0. So it is a null set. So A is 0, not equal to 0. So m star of 5, which is equal to 0. The next one, if A is the subset of B, then m star of A, which is less than or equal to m star of B. So by the definition of outer measure, we will say that A is contained in B, then m star of A is less than or equal to m star of B. So the next fourth one, for every x is greater than, x is belongs to R, then x is belongs to in. So for proving that let us take x which is belongs to in. This is nothing but x, we will take x comma x plus 1 by n for any n. L of in, which is equal to 1 by n, because you will subtract from second one to first one, that is x plus 1 by n minus x, we will find out the result 1 by n. So infimum of summation of L of in, which is equal to 0. So the given class that becomes m star of x equal to 0, that is the final one. The next is example, show that for any set A, m star of A, which is equal to m star of A plus x, where A plus x, which is equal to y plus x, is that y belongs to A, or prove that the outer measure is translation invariant. The proof of this example, for each epsilon greater than 0, there exists a collection in such that A is contained in collection of in, and m star of A is greater than or equal to summation of L of in minus epsilon. That is equation 1. The second, already it is given A is contained in union of in. It is the by using the Lebesgue outer measure, and then here you will be adding x on both sides. A plus x is contained in union of in plus x. This implies m star of A plus x is less than or equal to summation of L of in plus x, which is less than or equal to summation of L of in, which implies m star of A plus x is less than or equal to m star of A plus epsilon. So the next one, m star of A plus x, which is less than or equal to m star of A from this equation. So that is equation 2. So but we will write up A, which is A can be written as A plus x minus x, that is adding x and subtracting x, and then introduce the measure on both sides, m star of A, which is equal to m star of A plus x minus x. So m star of A, which is less than or equal to m star of A plus x, that is third equation. So from the second and third we will find out m star of A equal to m star of A plus x. Theorem number 1, that is prove that the outer measure of an interval equals its length. So the first case here, the two cases here. The first one, suppose that I is a closed interval a comma b for each epsilon greater than 0. We have m star of closed interval a comma b which is less than or equal to m star of a comma b plus epsilon which is less than or equal to b minus a plus epsilon. So this implies m star of a less than or equal to b minus a, that is equation 1. So from this we will say that m star of I which is less than or equal to L of In. The next in, for every epsilon greater than 0, I may be covered by the collection of intervals in such that m star of I greater than or equal to summation of L of In minus epsilon, where In which is equal to An Bn. In is nothing but the interval, closed interval An comma Bn. So next the sub interval, that is L of In dash, that is equal to, let us take this interval, that is equal to An minus epsilon to n comma Bn, where union of In dash is superset of I. So by the Borel theorem, if that the theorem is says that if A is a closed bounded set in R and A is a subset of union of alpha belongs to I G alpha, where the set G alpha are open and then I is in some index set, then there exists a finite subcollection of the set that which says Gi I which is equal to 1 comma 2 comma and so on n, whose union contains A. A finite subcollection of In dash says J1, J2 and so on Jn, where Jk which is equal to Ck comma C suffix k comma D suffix k covers I, which is Borel theorem. From this we will take, suppose that Jk is contained in any other, and supposing that C1 is less than C2 is less than and so on Cn, Dn minus C1 which is equal to summation of dk minus Ck minus summation of dk minus Ck plus 1. So Dn minus C1 which is less than summation of L of Jk, that is interval. So now m star of I which is greater than or equal to summation of L of In minus epsilon, this is nothing but the outer measure. So here I will introduce a subsequence here which is greater than or equal to summation of L of In dash minus 2 epsilon which is greater than or equal to summation of L of Jk, then Nk which is equal to 1 minus 2 epsilon, and then which is greater than or equal to Dn minus C1 minus 2 epsilon by 2 by equation 2. So from this we will say that m star of I greater than b minus a minus 2 epsilon. So m star of I which is greater than L of I minus 2 epsilon. So b minus a is now taken as L of I. So m star of I greater than L of I minus 2 epsilon. From this we will say that m star of I is greater than L of I, that is equation 3. From equation 1 and 3 we will get m star of I which is equal to L of I. Next case, suppose that I which is equal to closed interval a comma b and a is greater than minus infinity. So if a equal to b, the result is true. Now suppose a is less than b, in this case we will prove again. Suppose that 0 less than epsilon less than b minus a, and let us take I dash which is equal to a plus epsilon comma b. Then again we will take m star of I which is greater than or equal to m star of I dash, that m star of I which is greater than or equal to L of I minus epsilon, that is outer measure definition, that is equation 4. But I is contained in I dash, that is equal to a comma b plus epsilon. Another interval you will create, that is I double dash which is equal to a comma b plus epsilon. So m star of I which is less than or equal to m star of I double dash. So from this we will say that m star of I which is less than or equal to L of I plus epsilon, that is equation 5. So from 4 and 5 we will say that m star of I which is equal to L of I. So in the similar case we will find out I which is equal to a comma, that is open interval a comma b, and then I equal to close half open interval a comma b. So next case 3. Suppose that I is infinite interval. Here the 4 cases is arises. So first one we will take, suppose that I which is equal to half open interval minus infinity comma a. So another 3 is my infinity comma a comma infinity, infinity to infinity, minus infinity to plus infinity. Another one half open interval. On the other cases we will take only one case, that is I which is equal to minus infinity comma a. The other cases being similar one. So for we will take m which is greater than k on any real number. So there exists k, that the finite interval I m, where I m which is equal to k comma closed half open interval k comma k plus m, which is contained in the interval capital I. So m star of I which is greater than capital M, and hence m star of I which is equal to infinity, that is equal to L of I. So m star of I which is equal to L of I. From this we will say that measurement of the interval that is equal to the length of the interval. That is the proof. Hence the proof. And the next one, a Lebesgue measurable or measurable set. Definition: the set A is Lebesgue measurable or measurable if for each set A we have take m star of A which is equal to m star of A plus E plus m star of A intersection C. That is, C is nothing but the complement of the measurable set E. As m star is subadditive for each A, if E is measurable, then we have take m star of A which is greater than or equal to m star of A intersection E plus m star of A intersection CE. The next definition is sigma-algebra. That is nothing but a class of subsets of an arbitrary space X said to be a sigma-algebra or a sigma field if X belongs to the class and the class is closed under the formation of countable unions and its complement. That is sigma-algebra. The next is algebra or field. So there we will, in sigma-algebra, that is the countable one. Here the algebra, it is a finite one. That is the difference between these two, that is sigma-algebra and algebra. Now we will see the algebra definition. A class of subsets of an arbitrary space X is said to be an algebra or a field if X belongs to the class and the class is closed under the formation of finite union and of its complement. The next theorem, under this we will be using this theorem, prove that the class script M, the class of Lebesgue measurable sets, is a sigma-algebra. Now proof. So now will be proved M is closed under the countable union and of complements. For this we will take the measurable set E which is belong to script M and the complement C of E which is belong to the script M by the Lebesgue measurable sets. The real line R which is belong to script M. Now if Ej is a sequence of sets in capital M, that is script M, then we will be show that E which is equal to union of Ej, that is nothing but the collection of measurable sets which is belongs to Ij. The next, let us take A be arbitrary set. By the definition of measurable sets, m star of A which is equal to m star of A intersection E plus m star of A intersection CE, that is equation 1. The next, replace the equation 1 in E by E1. We get m star of A which is equal to m star of A intersection E1 plus m star of A intersection CE1, m star of plus m star of A intersection CE1, that is equal to m star of A minus m star of A intersection E1, that is equation 2. The next one, again we will be replacing E by E2 in the first equation and A by A plus A intersection CE1 in equation 1. We get the result, that is m star of A intersection CE1 which is equal to m star of A intersection CE1 intersection E2 plus m star of A intersection CE1 intersection CE2. The next one, from this we will say that m star of A which is equal to m star of A intersection C1 plus m star of A intersection E2 intersection CE1 plus m star of A intersection CE1 intersection CE2. Continuing in this way, in general, for n greater than or equal to 2, m star of A which is equal to m star of A intersection E1 plus summation of m star of A intersection EI intersection over complement of EJ plus m star of A intersection over CEJ. So, m star of A which is equal to m star of A intersection E1 plus summation of m star of A intersection EI intersection complement union over J less than I EJ plus m star of A intersection complement of union over J equal to 1 to infinity CEJ. The next m star of A which is greater than or equal to m star of A intersection E1 plus summation of m star of A intersection EI intersection complement of union of EJ plus m star of A intersection complement of union of EJ. So, because here m star of A which is less than or equal to m star of B, if A is contained in B, using this we will derive this, that is less than or equal to m star of A intersection union over I equal to 1 to infinity EJ plus m star of A intersection complement of union of I equal to 1 to infinity EJ. This is greater than or equal to m star of A. This is equation 3. So, for any n, we will find out union over I equal to 1 EJ intersection complement of union over J less than I EJ, which is equal to union over I equal to 1 to n EJ. Hence, we have find out the equality in equation 3. So, we have union of I equal to 1 to infinity EJ is a measurable one. Next theorem, if EJ is any sequence of disjoint measurable sets, then prove that m star of union of EJ which is equal to m star of summation of m star of EJ, so where I which is equal to 1 to infinity, or that is m star is a countable additive on disjoint sets of m script m. So, the proof of this, that is m star of A which is greater than or equal to m star of A intersection union of EJ plus m star of A intersection complement of union of EJ which is greater than or equal to m star of A. This is the generalization of the previous theorem. So, we will take union of IEI I equal to 1 to infinity. In equation 1 we will get the inequality result. So, the set EI is a disjoint one. The next theorem, prove that every interval is measurable. The proof is, suppose that the interval to be of the form half open interval A comma infinity, any one we will take. That is, there is other, it is the similar case, the proof is given the other types of intervals. For any set A, so we will show that m star of A greater than or equal to m star of A intersection minus infinity comma A plus m star of A plus intersection of half open interval A comma infinity. So, which is greater than or equal to m star of A, that is equation 1. So, the next let us take A1 n of the set A1 which is equal to A intersection open interval minus infinity to A, and A2 which is equal to A intersection half open interval A comma infinity. So, A1, A2 you will derive. A1 is A intersection half open interval A minus infinity to A, and A2 which is equal to A intersection half open interval A comma infinity. So, then for any epsilon greater than 0, there exists an interval In such that A is the subset of collection of In. Then m star of A which is greater than or equal to summation of L of In minus epsilon. This is nothing but the outer measure definition. Let us take In dash. So, another one created In dash which is equal to In intersection half open interval minus infinity comma A, and In double dash which is equal to In intersection half open interval A comma infinity. So, that L of In which is equal to L of In dash plus L of In double dash. So this is the collection of intervals L of in which is equal to L of in dash plus L of in double dash, that is equation 2. So then A1 is the contained in union of in1 in dash, A2 is contained in union of in double dash, already you know. So from this we will say that using the measurable set definition, Lebesgue outer measure m star of A1 plus m star of A2 which is less than or equal to summation of L of in dash plus summation of L of in double dash. So from this we will say that by 2 we will be say that less than or equal to summation of L of in. So m star of A1 plus m star of A2 which is less than or equal to m star of A plus epsilon, which gives the proof. Smallest sigma algebra. So let us take A is the class of subsets of space X, then there exists a smallest sigma algebra S is contained in A. We say that S is the sigma algebra generated by A. Already you know what is the sigma algebra. Sigma algebra is nothing but which is closed under the countable union and of complements. So here from this sigma algebra, any one smallest set of sigma algebra S which is contained in A, we will be say that sigma algebra generated by A. That is smallest sigma algebra definition. So using this we will derive the one of the theorem. Let A be the class of subsets of the space capital X, then prove that there exists a smallest sigma algebra S containing A. The proof is, let us take S alpha be any collection of sigma algebra of subsets of X. Then by the definition of sigma algebra, what is the definition of sigma algebra? Sigma algebra is closed under the countable union and of complement. So from this we will say that S alpha is closed under the formation of countable unions and of complements. So therefore intersection over alpha, S alpha is a sigma algebra. S alpha is nothing but the smallest sigma algebra. From this we will say that intersection over alpha, S alpha is a sigma algebra. But there exists a sigma algebra containing A, which namely the class of all subsets of capital X. So taking the intersection of sigma algebra containing, we will know the intersection that is very smallest one. So we get sigma algebra that is necessarily the sigma smallest containing A. So that is the proof. The next is Borel set. So B is the sigma algebra generated by the class of intervals of the form closed half open interval A comma B. Its measure are called the Borel sets of R. So under this one of the theorem, prove that B is the Borel set, B is contained in script M, that is every Borel set is a measurable set. The next one is the sigma algebra generated by each of the following classes: the open intervals of the open set, the G delta set and F sigma sets. The proof is, since the first one, since the class of measurable set is sigma algebra, already you know, and then every interval is measurable, this is also will know. So from these two statements we will be say that every Borel set is measurable. The next one, let B1 be the sigma algebra generated by the open intervals. Every open interval, since it is a union of a sequence of intervals of the form half open interval A comma B is a Borel set. So B1 is contained in B. So the next, but every interval half open interval A comma B is the intersection of sequence of open intervals. So B is contained in B1, that is equation 2. So from B1, first equation and second equation we will get B which is equal to B1. Since every open set is the union of sequence of open intervals, and the second result is also follows, that is since G delta B the sets and F sigma sets are formed by open sets and using only the countable intersection and complements of the sets. So the three results are following. Similarly, B is the sigma algebra generated by the open intervals. The open set G delta set and F sigma set is also measurable sets. Next definition, for any sequence of sets Ei, limit supremum of Ei which is equal to intersection of union over I greater than n Ei as n equal to 1 to infinity. Limit supremum of Ei which is equal to union of intersection over I greater than n Ei as n equal to 1 to infinity. So the theorem, using this definition we will derive this theorem. Let us take L, that is the theorem statement. Let Ei be a sequence of measurable sets, then prove that first one, if E1 contained in E2 contained in and so on, we get m of limit of Ei which is equal to limit of m of Ei. The second case is if E1 is superset of E2 which is superset and so on, and m of Ei less than infinity for each I, then we will prove m of limit of Ei which is equal to limit of m of Ei. The proof is, let us take f1 which is equal to E1 and fi which is equal to Ei minus Ei minus 1 for every I is greater than j. The next one, from this union of Ei which is equal to union of fi we will say. And then the set fi are measurables and disjoint also. So, m of L of En which is equal to m of union of Ei. That is equal to summation of m of fi which is equal to limit of summation of m of fi. That is equal to limit of m of union of fi. So, m of limit of En which is equal to limit of m of En. The second proof is, let E1 minus E1 which is contained in E1 minus E2 which is contained in E1 minus E3 and so on. So, by equation 1, from the case of first case, m of limit of E1 minus Ei which is equal to limit of m of E1 minus Ei. That is equal to m of E1 minus limit of m of Ei. That is equation 1. So, but limit of E1 minus Ei which is equal to union of E1 minus Ei. That is equal to union of E1 minus Ei. That is equal to E1 minus intersection Ei. That is equal to E1 minus limit of Ei. Taking the measures on both sides, we get the result m of limit of Ei which is equal to limit of m of Ei. That's the proof. Thank you one and all.